Hello and welcome back. So let's move now to the next two topics now on a theory of the theoretical background of unsteady RANs. So we're going to talk about steady unsteady physics, time scale separations. But let me show you something. So here we have these two solutions, and we're comparing RANS and URANS solution. As you can see, exactly the same solutions, or probably very, very small differences, and we're validating the results, the classical flat plate case. The only difference that we have here, it is that here, iterative marching, we don't have time, we're making the hypothesis that my solution, that mean doesn't change in time, and here we have time, that maybe that mean quantity change in time, I need to iterate in time, will be probably longer, but now you are time accurate. Due to that averaging, we might not resolve those scales, So, but still, the average solution, it is okay. But many people, when they're doing URANS, they will like to see, they would like to see those fluctuations. So here I have now this animation, and I added here a tripping, a forcing. Now this is exactly the same flat plate to have fluctuation. This is a forcing. So many people would like to have that, or the nice structures that we see in some DNS. To do that is really, really difficult now in some cases, but the idea is pretty much the same. So look at that. Here, by just looking at this profile, I know that my solution is correct. I'm not matching this theoretical profile. And to show you something also, let me go back here also. Let me go here. I have some figures that later we're going to show you, but these are the famous fluctuations that I'm talking that people would like to see. This stuff in an URANS simulation is completely average. You are not going to see this. If you see this, it's just a coincidence. Also, you are using a very fine mesh, very small times, but everything is average. Stuff like this, URANS, pretty much that is the goal. That's what we want to do, and you can see that it's working very well, but you are not going to see that. So that was a small parenthesis just to show you scenes in action, movies, figures, that usually people prefer that. So now let's address these two topics. RANS and URANS, steady and unsteady physics and solvers. It is a little bit more complicated than that, but let's make it simpler. So we have seen that our equations are this. Main difference in URANS is that we have time derivatives. The rest, it is exactly the same. Doesn't matter CFD solver that you use, set in the case is exactly the same. You only have time, some small nuances that how to choose time sets that we're going to see that in the tutorials. Modeling here, exactly the same. But from where this unsteadiness is coming, a big question, and usually it can come from the physics. So you have a physics that is truly unsteady. It can be due to moving bodies, can be due to multi-phase flows that you have different phases, and usually multi-phase are unsteady nature, can be due to buoyancy. Buoyancy also you have time. It can be rigid body motion. There are many reasons. But if you have that true unsteady flow behavior, you need to add time. It's strongly recommended. You can use a steady hypothesis, but your result will be questionable because you are not resolving the actual physics. That is the physics, and for that physics you can have different solvers. You can have an steady solver on a steady solver. So moving from that, and a reminder about in URANS that we have the mean that is changing in time. You have those fluctuations. We have seen that the goal of this averaging, is just to remove that. And if your physics is truly unsteady, you are going to have that mean oscillation. And if you are lucky, that averaging technique, the Reynolds averaging, is not going to remove that. It's that spacing that we have between small large scales that we mentioned. It is the spectral gap. And here we have a movie, and just to show you that in this case, this is a death simulation, by the way, what you're seeing here. Look at that. At the beginning we have a URANS like behavior. You don't have the small scales, and then boom, it is triggered that less like behavior. and you have all the scales and vortex stretching and breakdown of vortices and so on. So just to look at again here, look at let URANS like behavior. So this is what you expect for a pure URANS. It doesn't matter the URANS that you use. Okay, some of them might give you something a little bit better, but this behavior, you are not going to get it with URANS. So some people have reported that kind of results. Honestly, a little bit questionable. I don't believe in that, but it can be, okay, it can happen, okay? Who knows? So, okay, let's move here. So when working with RANs, URANS, okay, and now a few questions that you should ask. So should I use the RANs, URANS? Should I use this hypothesis or the other hypothesis? So if you are finding, you find that wall, you don't know what to do, okay, go down the wall or climb the wall, okay, try to ask yourself this question. How well does the steady model hypothesis capture the flow physics, and how accurate are the quantitative predictions obtained in the analysis, okay? So if you can answer in a positive way any of this question, you need to use, it means that your flow is stronger on a steady, you need to use the unsteady approach, URANS approach, okay? Additionally, okay, besides the physics, steady or unsteady, also consider the computing time, okay? So sometimes that can be limiting, okay? So I mentioned now as a rule, is you're working into the, go ahead, you do everything unsteady, to the, it is very cheap. 3D, you will find that limitation depends on your resources, okay? But this is, consider this. Another question that you should ask, I think we already addressed that in CFD cookie 1, is what kind of mesh should I use? Word resolver, word modeling, okay? And talking about that, so if you're working 2D, go word resolving on steady. That is inexpensive. If you're working 3D, stop, think about or measure now your computational resources, because that can be very expensive, and everything that we're doing revolves about commodity, very valuable, okay, which is time, okay? Time and space, your time in your computer, everything is about time, okay? And that makes things very expensive. So to talk about the physics, so look at that. We have this case, the flow about a circular cylinder, Reynolds 200. I hope we're very familiar with this. Okay, so you have studied fluid mechanics, fluid dynamics. You know this case that at 200, or you have the von Karman street, and this physics, it is truly unsteady. There is nothing to do. Okay, but to solve the physics, there is no problem. You can use unsteady solver, like in this case, you are solving the right physics, you are capturing the frequency if you use the right time step, by the way, but you also can use a RANS solver with no problems, okay? However, look at that. What happens with RANS solvers, steady RANS, is that they are not capturing the physics, the frequency. So you have a solution, but it's not accurate in time. However, if you are interested in average solution, this will be something acceptable. Might be, I'm not going to say yes, it's absolutely acceptable. It might be, in many cases, it will be acceptable, but there is no problem. On steady physics, you can use steady solvers, but it's up to you because results can be questionable. On steady physics, you can use URANS solver, and that is the right solver that you should use to capture the physics, but things can get expensive. So here also, besides these colors, we have an integral quantity. We measure coefficients, drag and lift, and look at the difference. On steady, pretty much accurate in time, okay? You can see that pinpoints that frequency, fantastic, okay? But when you look at steady solvers, highly underpredict. It's going to give you a value, but it's underpredicting this. So in this case, this is not very accurate, but it's giving you a color. So this solution, maybe you can use it to initialize the unsteady solutions, and you save long initial transient, which, by the way, here I'm comparing both cases in terms of iterations, not time. I don't have time in the steady, so I cannot do it. But in the unsteady, I have time, but also I have my iteration, my time steps. So that is how I'm comparing. And if we look at lift, okay, so the mean value is 0. So, well, the steady works very well, but doesn't capture the variance or the minimum and maximum. Okay, so it's up to you. Look at the difference. So be very careful. So before using a solver, think about your physics. So that is the first step. Formulate your problem, know your physics. So if your physics is truly unsteady, you should go for an unsteady solver. So be ready to pay the high cost of those simulations. But now let's make things more interesting. So let's take a look at a steady physics. So in this case, -20, in this case, there is no von Karman streak. It is truly steady. So industrial applications, you don't find very often this. So in this case, you can use a URANS solver, but also a RANS solver with no problems. Okay, so here should be RANS. Okay, and there is no problem here. Likely, very likely, the RANS solver will converge more faster, so you save time. Here it will take more iteration. It will be slower, or sometimes it can be even faster. You never know. You need to run personal experience. Honestly, if you have a steady physics that you are absolutely sure that it's steady, low Reynolds, go for on a steady solver that sometimes, many times they are faster, and if they are slower, it's not by not that much. So here you capture the right physics and you have more stability. But in any case, it's up to you. Okay, so this is the difference. Now, if we look at forces, see that both of them, they are very accurate, so give the right value, or at least when you compare. Interesting to look at here, look at the number of iterations that we have and see that the steady, let's say that probably in 400 iterations it converges, but the unsteady doesn't take that long. Okay, so 600 iterations probably, so see that a small difference. Okay, and same when we look at the lift coefficient. I want to point out that behind this one also, we're looking at iterations. Remember that in unsteady also you are going to have a sub loop, more iterations, so you are going to crunch much numbers here. Okay, so if you measure your floating operating points, this you crunch more numbers. So don't take it so light, like, yeah, this is faster. Go. So yeah, they are similar, but you are crunching much numbers. But in any case, you have here a nice comparison. So this is when it comes to steady and unsteady physics. Hopefully it's clear to you. Know your physics. Okay, so here and you have a nice example. I think this is something that we should address in another video and look what is happening, what happens when you change time step and so on, how you add diffusion, time diffusion, and everything. So that will be another video. So now let's talk about, to end this video, time scale separation, that spectral gap, that problem that we have in URANS simulations. So in URANS now, we have seen that we can see the mean flow as a result of a time average or ensemble average. You take that quantity, apply that, remove scales. Then you have here this separation T1, T2. You have to be very careful. This T2 is close to T1. Also is going to average that to remove that, and you are going to lose all that unsteadiness. And that is the issue why you don't see less like results with URANS, because those very small fluctuations are removed by your averaging technique. Okay, so talking here now, so well, a little bit what we're seeing. So if you cannot satisfy this requirement that T2 have to be larger, as we mentioned, that now the averaging is going to simply remove that. Okay, and this is due to the lack of separation between those scales, and this separation between flow scales and turbulent fluctuations, that what we know about a spectral gap. Okay, and well, this spectral gap is not large enough. Well, I'm repeating the same though. It is not possible to distinguish between turbulent fluctuation, flow scales, large scales, and your standard averaging remove everything without numerical diffusion, and that's why now you don't see anything. Okay, you can overestimate the physics. So in those cases, now we can say that your fluctuations and mean quantities are strongly correlated, and that's why, boom, your average remove everything. So URANS simulations now, as I have been saying, might give you the misleading impression that they are accurate in time. Okay, however, be careful, because there is a lot of numerical dissipation. You're going to see when you do a deep study, and we're going to work in some of the videos, you're going to see that there are some differences, some dissipation. However, you look at mean values, they are similar. But frequencies, instantaneous values, they will be different. So it can be very large, can be very small, okay? Okay, so some interesting references regarding SRS-like behavior of URANs. So talking about this, that some people report, and I mentioned that sometimes I see some research and studies papers that they show URANs. No, we're using URANs method, and then they show some results on that they are resolving. Or you see that vortex extraction. I very suspicious about that, but because it's difficult to get that, or if you get it, probably you are overdoing that problem because you need very fine meshes, small time steps. So why not switching to a day's lesson? Yeah, you will have the same computational cost. And here we have these interesting references, okay, about that. So this one, no, is very nice. I love the title, The Myth of URANS. So we're going to look at that at the PDF. But the second one is very interesting. Okay, you have the authors, and here you have the Spalart, okay, the Spalart guy, sorry, Philip Spalart, and very interesting. I strongly recommend it. A very nice comparison, the first one. And just to show you, from the paper by Spalart, okay, it's a paper about this, okay, that iterator. So look at here that we have a comparison between. This is the case of the cylinder, no? So we have here a comparison between a steady solution. So look at that the steady is not going to give you any unsteady information, just an average information. Then on a steady RANs, now you get something. And on a steady RANs, if I will recall, this is a finer mesh, or okay, no, this is 2D. Then you move to 3D SST. So yeah, finer mesh, 3D, and kind of resolve more structures. But yeah, still it's not there. But what is interesting, look at that, the diffusion, these two, look at that, the space in between all these vortices here. It's not that much. There is not much diffusion. Now look at when you move to another approach, we call SRS, scale resolving simulation. Look at the wake, how much diffusion, Here, okay, there is a lot diffusion, so it can be species diffusion, polyton transport diffusion, thermal diffusivity, whatever, but you have that diffusion that you don't see here. Okay, so qualitatively speaking, you are missing that. However, if your average values, they will be similar. Okay, so this is the main difference. This is, okay, what you are missing, not to say all the frequencies and so on. Also, just to show you another result here that we have SRS. No, this is a less simulation now. And look at that, less simulation, they strongly depends on the mesh. So different meshes, different results. As expected, later we're going to see a little bit of theory, and then in another cookie, but in the formulation, you have the Greek spacing. So clearly you can see different meshes. Instead, in RANs, nowhere that grid spacing appears, except for the SAS. Remember that we studied that SAS model, K omega SAS. There you have that grid spacing. So that method might be sensitive to that. But this behavior, changing different grids, you are not going to see this in RANs as well. Okay, RANs, URANs. You are going to see the same results. And remember that you have two equation models. You can compute integral scale, length scale by a combination of those variables. And if you do that, this will be exactly the same when you plot that in different meshes. And talking about the URANs and that behavior, the importance of having that spectral gap, okay, that it might happen when you're computing frequencies, you entirely miss that frequency. So here, it doesn't matter the problem, by the way, that I'm showing you here, but we take that time signal here, okay, standard coefficients for that model, and look at that, I don't see any dominant frequency. Okay, even if you have some unsteadiness, you are going to miss some important frequency. And then by adjusting the coefficient, in this case C mu, look at that, now one capturing a frequency. Maybe the dominant, I don't know. But just to mention that also you can control that behavior by adjusting coefficient. And we saw in the previous cookie that can be done. C mu in this case, particularly in this case, I decrease C mu, okay? and now I managed to capture that. And there is some research on that. So some models, URANS models also has been improved. Now the formulation has been improved by adding this coefficient or a blending function, something like that, that can calibrate this coefficient. Or in your case, if you want to improve, you can do it. Okay, do it with care, but it can be done. So here we look at two cases now, the URANS and the less case. By the way, just to point out that this is a square cylinder, so triggering this effect here is much easier than triggering that effect here. So we were talking about that the flow here remains attached, and so it's very tricky. Okay, here it's much easier now because you have that separation here in that sharp angle. But look at that, your trigger, we use this less model, and this is the behavior. Okay, you have all the vortex stretch and so on, but the RANs, the URANS, the unsteady RANs, you have this. And look at now at the width of the wake. More dissipation here, you have that dissipation. Okay, so it's important if you are transporting quantities, URANS might underpredict that. However, now you will have some nice behavior here. No forces, mean quantities will be okay. Look at that. Also, you let it run in time. You have more spreading, but if you compare this with this one, you have more dissipation. Okay. And well, here we compare all the different methods, laminar, less, and so on. So pretty much the same, the less, and there you go. Okay, so nice comparison. But I was talking about this. Be careful about this. Now then you have everything. So the colors can be nice, but then you get integral quantities that are different now. So all these models, they were closed. The laminar, the DNS, in this case, the unresolved DNS, because the mesh by no means is a good mesh for our DNS. You have this. Okay, so in this case, it's highly over predicting the value of the drag, but also the value of your frequency. So it's true how numbers related with the frequency and so on. Well, so just to end here, some comments about URANS and so on. And well, just to mention that the word for today of turbulence model in industrial CFD is RANS URANS. Okay, SRAs less is still very expensive. Okay, computer power is increasing. Okay, no doubt about that. I still remember 10 years ago computers that were using and with what I'm using today on my desktop. Now that I have a desktop computer with 128, 10 years ago that was pretty much that was 2 or 3 computing nodes, and 20 years ago that was a complete cluster. It is increasing, no doubt about that. But the issue is that time. You have that commodity. It's time. You need to do a lot of timestamp and so on. So that's why URANS still are. You can use larger timestamps, so on, finer meshes. Okay. Then also there is a clear trend to move toward nonlinear eddy viscosity models, okay, and algebraic Reynolds stress models, and we study those models now in CFD Cookie too. But there is this clear trend, and everything's trying to stay away of the less days because they are still expensive. So well, looking again at our progression, our pyramid here, okay, which is not a pyramid. In any case, study RANs, we're moving RANs, and as you see, we're paving our way to this. That will be some other videos. Okay, so with this I end this, and I would like to now to revisit, because we have here this references that I put there, and let me go here and visit this one, the URANS solution with less like behavior. So this is one by mentioned Felix Spalart, and very interesting. Now, so in the video description you have the link to download this one. So I recommend you to read this. So it's talking about all this behavior, RANs, URANS, what happened here and there. Okay, remember, you need to digest the whole theory. Just get the gist here. Highlight some notes. So look at that in this reference start to talk. They talk about spectral gap and so on. Okay, and okay, computational time and everything, and well, here we have this interesting that for URANS does not have a rational theoretical background justification, okay, because it's not solving those time scales. So, and somewhere here they're mentioning that it's just merely a coincidence that you get good values. No, even this paper is old, the same applies today. Okay, there is no formal justification why you should have less light behavior or you should have good behavior, because they are not resolving that. Okay, so more comments there. So this is interesting to read what I was mentioning, frequencies. So just look at what you have here now. Okay, so here is a RANS, then you move to something scale resolving or still URANS, and by coincidence, right now I'm running a simulation. It's not the same case, but look at what, this is a less simulation. I'm talking about that in this kind of simulation, sometimes you can have energy dissipated, okay, and somehow you need to add energy just to trigger that separation. And I know this is what is happening here, okay? This fluctuation, this is stuff, know that CD you have, and in this case I'm running Fluent. I know that if I use OpenFOAM it will be exactly the same behavior. So very interesting paper, recommend to follow, read it, just okay, give it an interpretation. But let me go here to the very end. Talk about now conclusions that now mention that a positive feature of URANS approach, for separated flows, that also solving separated flows with URANS and getting right results, theoretically speaking, shouldn't be correct, shouldn't be done. Okay, so I mentioned here in general 3D solutions are superior to 2D ones. Okay, very important also that, okay, they have found, and also personally speaking also, it's better to go 3D than 2D. And one thing that 2D tends to be very energetic, way motion energetic, and those can be one of the reasons why you are not capturing right behavior or you have some strange behavior. So in 3D, capture right physics, okay, but okay, they still did that effect in the span-wise direction is still very unpredictable. What happened that vortex extraction, okay? Appears that, okay, there is uncertainty, okay, distinction of URANS less, and also to show now globally URANS approach is not yet understood in depth and suffer from a repeated non-predictable behavior in different solutions and different models. And you can confirm this, okay? You run that, I have confirmed that, talking about the spans-wide behavior and so on. So there is a lot to do when it comes to RANs, to URANs, to precisely see what is happening there. Okay, moving to this, the myths of URANs, very nice. I love this paper, also interesting. So similar observations to the one by Spalart. Okay, they talk about the myth that, okay, URANs sometimes resolve the spans-wide dimension and capture some behavior. They work for URANs, or when you don't have a strong separation, they also capture some frequencies and so on. And pretty much all the authors, they get to the same conclusion that it is merely a coincidence, something in coefficients. There is no theoretical background to justify that. That with less days can be done here. It is difficult. So I have my own comments here. Very interesting, this one, to specify exactly what tool and solution is supposed to make it impossible to determine. Several authors have, okay, a little bit the triple decomposition or phase average that I talk about that. Okay, so the reason why unsteady arrives in certain case and not in other is not understood, other than a general idea that is related to how unstable the flow is and how dissipative is the model. Now, so something similar to what Spalart it is saying. Question, okay, the mechanism, how to trigger that, how to put that. So we keep reading here, compare different models, unsteady, and let me move. And here we go into conclusions. Now, finally, we conclude here that conventional RANS models were developed using a single scale assumption. So those clauses justify where any resolve unsteadiness resolve a spectral gap. You have an spacing. If you have that spacing has been repeating, everything will be removed. Okay, or equivalent, you have large scale. So when you have a strong unsteadiness, okay, so if you put an aerodynamic body and then you have the blunt body, you will see the difference. That the blunt body is quite easy. The aerodynamic body, the sliding body, is very tricky to trigger that. Okay, So pretty much now that is the gist of this paper. And now here we have a few applications. So I took 3 or 4 applications, general applications. So I look for them. Some of them, no, it's not because they are super good. All of them, they're going to tell you the same. Probably know the authors, okay, and some of them. Some others will just pick one random, but that's all. So we read this one now, comparison different models for pollutant dispersion. So look at that, we're talking about diffusion, and we address that in the wake of the cylinder, that URANS, the diffusion is less. And you read this one, this nice case. Okay, by the way, this is a nice validation. There is some experimental data. They compare the wake, but then at the conclusions, they said in this specific case, okay, comparing the models, they found that URANS is cheaper than less, okay, which is expected. Okay, different measures, by the way, okay, when it comes to measurement requirements, but it's not a suitable replacement for air pollution problems, okay, because it doesn't capture the diffusion, okay, in this specific case. Then we have another application, no validation, and in this case, it's pretty much also this one is about thermal diffusivity. Okay, this one, pollutant dispersion, thermal diffusivity. Same stuff, okay? So here also they do a study, different models, who run less and so on. But in this case, very interesting. And I say it doesn't mean that this is wrong, okay? It can happen. That they found that URANS results show general agreement with less data, okay? And yeah, now you read a lot of paper, you will say that this shouldn't happen, but in this case, it happens. Who knows what is the reason? Coefficients and so on. Okay, so they have a smaller set, but okay, conforms now to the uncertainty that they claim is acceptable. Okay, URANS, so that implies that URANS. Okay, here the author say that the URANS is promising candidate 3D modeling approach for this kind of application. Probably the application, the dimensions, who knows? Okay, but look at 2 authors, completely opposite conclusions regarding diffusion. And now we move to another one. Okay, so here again, comparing, so SRANS, steady RANS, URANS, unsteady URANS, SAS, scalable, adaptive, and so on. So in this case, prediction now in high-rise windows, so wind engineering. So pretty much the same discussion now. Now also there is a strong focus in SAS, that is that model that probably seems the most promising one when it comes to RANS and so on. But same study. Okay, actually, this is also a nice study that reproduces some of the results. But here we're talking about the wake. Okay, so they measure the wake. For some cases, they found that URANS resolve well the wake, doesn't resolve well the wake, and so on. Okay, so I put some of my own comments there, but let me move to the conclusions. And basically, in this case, now self approach the SAS, the scalable within flow. Remember that we talk also that sometimes you need to add that forcing. So in this case, they added a forcing in the inflow, some fluctuations, and within flow they managed to get a good agreement with experimental results. In a sense of this technique, now the URANS behavior predominated in the wake, that is that diffusion. Okay, suggesting now that the unsteadiness due to what you are resolving about the body is not sufficient to activate to trigger the behavior, the type, the less type behavior. Okay, so here they talk about that wake behind that. In some cases, the SAS match well the less or the experimental, and in other cases, no, it was closer to the URANS, that it was very dissipative. And by the way, the steady was off of everything in this case. So look at that. Many authors, a lot of to read about that. And now we move to this one. Same stuff, comparison this runs less. Probably this is an extreme one. So we take a flat plate, it can be a wing and an air or whatever, but at high incidence. Now we know here we have separation. For sure, URANS should fail entirely. If you want to capture frequencies, average values, likely probably you will be there. So let me go right ahead to the conclusions here, and there you go. So pretty much what I just mentioned, they have here now. So expected RANS computations were not able to capture unsteady vortex shedding, okay, bluff body, 2-dimensional RANs led to this steady state, no 2-dimensional structures were observed, so I was expecting that. In contrast, the asymmetric vortex shedding was resolved with this and less. Then this less with the carry out a comparison, different meshes, and this sometimes failed to solve something, but it failed when it came to the RANS mesh close to the body, where the RANS approach was applied. That is talk there, where they talk about that in there. So this is it, okay? So 4 different applications in the video description. Now you get the video, but just search the way that you will find a gazillion of applications. So hopefully I address all the small nuances that we have in URANS. As you see, it's pretty much the same, nothing changed, but now you need to address, and mainly is that spectral gap, then the diffusion, and remember, you can change coefficients to adjacent. So that's all for this video. Thank you for your attention, and see you in the tutorials.